Thank you very much for this introduction. It's a great pleasure to be here. So I would like to start maybe with this picture. So I've been 2 years ago, exactly 2 years ago, to Nepal. So that time it was physical. That was very shortly before the pandemic has begun. So I think this has really been a wonderful experience and unforgettable. So I think I will do my best to try to get to Nepal again sometimes in the future when the circumstances allow it. So you heard a great session from what I understood today in the morning. It was a little bit too early for me, so I will then watch the recording about graph neural networks. And I would like to talk again about graph neural networks, but probably in a slightly broader context, and try to present it from a perspective of geometry. So how can we derive graph neural networks? And as a matter of fact, many other popular architectures that are probably now commonly used in deep learning and in the academia, in the industry, from first principles of symmetry. And then in the second part of the talk, I will talk about some more recent work that we've been doing, trying to connect graph neural networks to notions from differential geometry, such as curvature and geometric flows. And then my collaborators, Chris Bodner and Fabrizio Frasca, will be talking about a slightly different approach, looking at graph neural networks through the perspective of algebraic topology, basically how you can do an extension of message passing mechanisms, taking into account structures that go beyond graphs, simplicial and cell complexes, and then also connecting it to some deep and quite mysterious results in graph theory, such as the reconstruction conjecture, and this will be the part on subgraph GNNs. So you can find more material here. So this, as you probably some of you might have seen, a blog post on Towards Data Science, a YouTube channel with recording of an entire course about geometric deep learning, a proto book that hopefully next year will be coming out with MIT Press, and many other materials on geometricdeeplearning.com. Now, I promised to start with symmetry, so let me start with this quote from Hermann Weyl, one of the greatest mathematicians of the 20th century. And he said, somewhat poetically, that symmetry, as wide or as narrow as you may define its meaning, is one idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. So Weyl himself was a mathematician. He studied mathematical physics, and he played a crucial role in creating the mathematical foundations of modern physics as we know it today. And he points to the fact that symmetry occupied a special place in science and art from the ancient times. And the word symmetry itself comes from ancient Greece, where it was used to somehow vaguely to convey the beauty of proportion in art and harmony in music. And for example, Plato considered the regular polyhedra that nowadays bear his name so fundamental that they must be somehow the building blocks of the material world. So he anticipated by about 2000 years our modern understanding of crystals in crystallography. And of course, geometry itself, you can argue that at least in the way that we know it, began in ancient Greece. And what we now call Euclidean geometry was in fact the only geometry known for more than 2000 years, originating in the seminal work of Euclid, the Elements. And what happened is that some of the assumptions of the Euclidean geometry, in particular the fifth postulate about parallel lines, defied any attempt to prove it. And what happened in the 19th century, maybe as an evolution of some previous attempts that were not successful, it brought the end to Euclid's monopoly, and it was really a remarkable burst of creativity that made geometry into probably some of the most exciting fields of mathematics. And it was first the development of projective geometry that was rediscovered by Poncelet in the beginning of the 19th century, and then first examples of non-Euclidean geometries that were constructed by Nikolai Lobachevsky, Janos Bolyai, Gauss himself, and his PhD student Bernard Riemann. So at the end of the century, an entire zoo of different geometries emerged, and mathematicians of that time were debating which geometry is the true one and how you actually define a geometry. So what makes something a geometry. And it obviously was quite an unhealthy situation. And in 1872 came a young German mathematician called Felix Klein. He was only 23 years old when he was appointed as a professor in the University of Erlangen in Bavaria in Germany. And he was, as it was customary, and probably still customary in Germany, to present a prospectus about his future research at Erlangen, which he published in a research paper that entered the history of mathematics as the Erlangen program. And in this paper, Klein proposed a radically different approach to geometry, namely studying it as a set of invariants or symmetries. So these are properties that remain unaffected under some class of transformation that was formalized using the notion of groups that he also contributed to develop. And then Weil, that I already mentioned with his poetic definition of symmetry, used these ideas to develop what he called the gauge invariants. And after a certain evolution with the discovery of quantum mechanics and certain generalization that was developed by Young and Mills in the 50s, it somehow proved successful to unify all the fundamental forces of nature with the exception of gravity. So this is what we now know as the standard model. The term itself is also from the 70s. And it describes all the physics that we know. Again, gravity doesn't fit this picture yet. And it is all described in terms of gauge invariance or this particular kind of symmetry. So I can here quote another Nobel-winning physicist, Philip Anderson, that it's only slightly overstating to say that physics is the study of symmetry. Now, at this point, you can wonder, what does it all have to do with deep learning? So I think it is connected very deeply, and I would like to bring up 2 points. First of all, I think there is no doubt that deep learning has created a revolution in data science over the past decade, and it made possible some tasks that maybe even 10 or 20 years ago would be considered science fiction. I personally would think that I would not live to see them successful. What is really working computer vision, speech recognition, natural language translation nowadays can be even done in an unsupervised way, playing intelligent games like Go, or maybe the problem of protein folding. So it's all nowadays possible thanks to these deep learning methods. On the other hand, we are not very different from the situation with geometries in the 19th century in the sense that we have a zoo of different neural network architectures for different kinds of data, but few unifying principles. And it's hard often to find relations between different methods. As a result, there is a lot of reinvention and rebranding of the same concepts, and sometimes even, unfortunately, bitter fights between researchers over priority. So we need some form of unification, some common ground or some common foundation in the spirit of the Erlangen program that Klein was successful in reconciling mathematics and giving it an important impetus forward, in particular affecting many fields in physics and category theory and whatnot. And this is what we call geometric deep learning. So its purpose is first to provide a common mathematical framework to study some of the most popular and successful neural network architectures. But secondly, and probably more importantly, it gives a constructive procedure and principled way how to incorporate prior knowledge into neural networks, and it will allow to build future architectures from first principles. And you can already see it in some, so many completely novel architectures are not, they do not appear every year, right? And yet we see in the past couple of years, armed with these principles, a lot of new interesting things, like, for example, equivariant message passing, that are now architectures very popular in computational chemistry. So this all builds upon these principles that I will be highlighting today. So the term itself, I can probably credit myself with inventing it when writing my ERC grant, and it was popularized in this 2017 paper in the IEEE Signal Processing magazine. Nowadays it's almost synonymous with graph neural networks, but I hope to show you that it's a way bigger umbrella term for basically everything that involves a geometric view on machine learning. So let me try to convince you why we at all need it, right? So if you look at machine learning, at least in some of the very basic settings, namely supervised learning, it is essentially or can be thought of as a function estimation problem, right? So we're given some unknown functions. Let's say that a function that takes in an input image of cats and dogs, and we observe it on the training set. So we have a labeled set of cats and dogs, and we know the labels of these images. And we try to find a function that fits well the training data that comes from some hypothesis class. And this way we can predict the outputs for previously unseen inputs. And again, image classification is a classical example in the domain of computer vision, but you can think of a lot other examples as well. Now, what has happened over the past decade or so is the coincidence of three main factors. So first of all, the availability of very large and high quality data sets such as ImageNet, that contains millions of annotated labels, annotated images, and appropriate computational resources, together with some architectural advances. And this has led to the design of rich function classes that, at least in theory, have the capacity to interpolate such large data sets. And neural networks appear to be a suitable choice to represent such functions, because as you know, even with the simplest choice of architecture, like the perceptron, which is a fully connected neural network, you can connect just one hidden layer, right? So you have two layers in this neural network, and it allows to represent a dense class of functions, or in other words, any continuous function can be approximated to any desired accuracy. So this is a property that we call universal approximation. Now, the setting of this problem in low dimension is a classical problem in approximation theory, and we have very precise control of estimation errors, very good bounds. So we can say, for example, how many samples and exactly where we need to take off a function in order to approximate it well. But it appears that these results are more or less useless when it comes to high-dimensional data. And you can quickly see that in even very regular and very nicely behaved functions, such as continuous Lipschitz functions, for example, what is shown here is a superposition of Gaussian blobs that are put in a quadrants of a unit square. So it's hard to think of anything more nicely behaved than that, right? And even here, you can easily show that if you increase the dimension of the space, the number of samples that you need to take to achieve certain error epsilon will grow exponentially fast with the dimension. This is a phenomenon that we often refer to as the curse of dimensionality. And unfortunately, it is not something that happens from time to time. It happens always in machine learning problems, because the data in machine learning problems, in most cases, is very high dimensional. So it's not 2 or 3 dimensions. How about thousands or millions, right? So the curse of dimensionality makes such naive approach to regularity useless, and the learning that is based on such notion of regularity in most cases impossible. And this is probably best manifested in computer vision. So again, this is the image classification example, and even tiny images tend to be very high dimensional. But intuitively, you see that there is somehow a lot of structure that would be thrown if I just take an image and parse it into a vector in order to give it to a neural network. Basically, a perceptron acts on vector data that breaks the geometric structure of the image. Now, what happens is that if I just take a shifted version of this digit 3, we know intuitively that it's still the same digit, right? But the vectorized input will be very different, and as a result, we'll need to show a lot of examples to the neural network in order to learn that shifted inputs must be classified in the same way. So we call this usually data augmentation. Now, in computer vision, the remedy to this problem came from classical works in neuroscience, in particular the work of Hubel and Wiesel that won them the Nobel Prize in Medicine in 1981 on the organization of the visual cortex, where they showed that brain neurons are organized into what they call the local receptive fields. And this served an inspiration to a new class of neural architectures with local shared weights. First, it was the neocognitron of Fukushima in 1980. And then, of course, the convolutional neural networks, the classical work of Jan LeCun. And this concept of weight sharing, which we'll revisit today several times, that you can share the weights across the image pixels, effectively solved the curse of dimensionality and made CNNs invariant, or as we'll define it more accurately, equivariant to object translation. Now, here's another example. So what you see here is a molecule of caffeine, and I hope that you had your portion during your lunch break. So this is a graph that models an atom. The nodes here represent, a molecule. The nodes here represent atoms and the edges represent chemical bonds. And here again, we can try to apply a neural network, for example, to predict some properties of this molecule that would be interesting and important in, let's say, drug discovery. So the issue here is that we don't have really a canonical way of vectorizing a graph. So in an image, we could take, for example, a column or a row stack of pixels. Here we can do any permutation of the nodes. There is no canonical way of doing it, or at least in most cases. So this will already make an imprint on the kind of functions that we would like to do, or the kind of architecture. So we'll be talking about permutation invariance in this setting, for example. And molecules are just one example of data with irregular non-Euclidean structure on which we would like to apply deep learning. And another example are social networks. So these are gigantic graphs with hundreds of millions of nodes and billions of edges, different types of interactomes or interaction networks in biological sciences, meshes and manifolds in computer graphics, and so on and so forth. So all these are examples of data that will fit into this general picture of geometric deep learning in the same principled way. Now, if we look again at this multidimensional image classification example that at the first glance seemed hopeless because of the curse of dimensionality, one thing that we can observe is that we do actually have additional structure that comes from the geometry of the input signal. And we call this structure geometric prior, and as we'll see, it's a very powerful general principle that allows us actually to address these dimensionality curse problems. And this has been, of course, done for decades now in machine learning, maybe without explicitly acknowledging it. So that's what we are trying to do here. We are trying to find some design principles that explain successful architectures and allow to develop new ones. So in our example of image classification, the input image is not just a d-dimensional vector. It's a signal that is defined on some domain omega. In this case, it's a two-dimensional grid. So I will denote the space of signals on this grid by x of omega. Okay, and the structure of this domain is captured by a symmetry group that I denote by this factor G. So again, in this example, it's the group of two-dimensional translations, and the group acts on points on omega. So the points are denoted here by U. I can move them around. Okay. And now in the space of signals, the action of the group on the underlying domain is manifested to what is called the group representation. I denoted by rho. So basically it's a function composition, right? And this representation, you can think again in this concrete example to make it more tangible. It's a matrix of size d by d that acts on our d-dimensional vector, right, or on our image. Okay, so it's simply a translation or a shift operator. So here we have decomposed our problem into three different objects. So we have a domain omega, right, with its symmetry group G. We have signals that live on this domain, on which the group acts on its representation. And we have functions that are defined on these signals that will, basically where the structure of the group will be manifested through what we'll call invariance and equivariance. Now I should say that the choice of all these different things is to some extent independent. So I can give you a grid and I can give you a different symmetry group. So it doesn't need to be translation group. It can be, for example, rotations and translations, or rotation, translations, and deflections. I will get a different architecture as a result. Okay. Now, the way that a group representation acts on signals depends also on signals. So, for example, a group representation, as we'll see, acts differently on vectors or on matrices, right? So here as well, depending on what kind of data I'm working with, I will need to be careful to consider different types of representations. And finally, the functions themselves, we can define different properties that they would obey. One of them is invariance. And we can say that the function is invariant under the action of a group is, as the definition says it, the output of the function is equal to the of the transformed input is equal to the output of the function on the original input, right? And a good example is the problem of image classification. So if I shift the cat around in an image, I don't care about where it is located. I still want to say that this is a cat, right? Another kind of geometric property of a function is equivariant function. So if the input and the output space of the function have the same structure, we can demand that the output of the function is transformed in the same way as the input under the action of the group. And a good example is image segmentation. The output here is a pixel-wise mask. So if I move the cat, I want the mask to move in exactly the same way. Okay, so this is what is called translation equivariance in this setting. Another type of geometric prior is what is called scale separation, and in some cases we can construct a multi-scale hierarchy of domains, for example, by coarsening our grid. So I have a new grid that is denoted here by omega prime, and this coarsening assimilates nearby points and produces also a hierarchy of signal spaces that are related by coarse graining operator P. And on this coarser domain, we can define our function denoted by f prime. A little bit unfortunate notation, it's not derivative, it's just another function. And we say that our function is locally stable if we can approximate it as a composition of the coarse graining operator and the coarse scale function. And what it does is that if the original function depends on long-range interactions on the domain, in locally stable functions, it is possible to separate the interactions across scales. And while maybe less glorified than symmetry in physics, it is actually a very crucial principle in physics as well. And this is what essentially allows us to do physics. And the example that I like to give is when I sit in this room, I'm surrounded by probably at least a quadrillion of molecules of different gases that form the atmosphere, and they collide with each other, they zip across the room. And of course, I don't need to simulate all this motion of molecules. First of all, it will be computationally intractable to understand, for example, how wind blows on Earth, right? So if I zoom out, I have a simple way of abstracting out these interactions and using, for example, computational fluid dynamics, or maybe even thermodynamics, statistical mechanics, to describe pretty reasonably well the behavior of gases. If I further zoom out to the cosmic scale, in order to understand the motion of Earth around the sun, I don't care about the composition of the atmosphere or anything else. At this scale, the Earth can be thought of as a point, right? So that's exactly the same idea, the same principle of working with different scales. So these two principles of symmetry and scale separation lead us to a very general blueprint of geometric deep learning that I hope you can see and recognize in the majority of popular deep neural architectures. So we typically apply a sequence of equivariant layers that preserve the structure of the domain, possibly followed by an invariant global pooling layer that aggregates everything into a single output. And in some cases, we also can create a hierarchy of domains by a coarsening procedure that is usually implemented in the form of local pooling in deep learning. And this is a very general design. We can apply it to different types of geometric structures, whether it's grids, more general homogeneous spaces, graphs, sets, manifolds, where it actually has two different manifestations, for example, in the form of gauge invariance. And this is what we call the 5G of geometric deep learning. Now, the implementation of these principles, basically the inductive bias that stems from them, you can find it in some of the most popular architectures that exist nowadays in deep learning, whether it's convolutional neural networks that you can derive from translational symmetry. That's what we'll do in this lecture. Graph neural networks, deep sets and transformers that can be derived from permutation invariance. Again, we'll do it as well. And maybe slightly more exotic architectures such as intrinsic CNNs or gauge equivariant CNNs that are now becoming more popular in computer graphics and vision. So I will start with graphs. And graphs, as you've seen before, are pretty interesting objects. And why they're so interesting? Because we can use them to describe practically any system of pairwise relations or interactions. And we can think of graphs everywhere from nanoscales, where we can, for example, model individual molecules as graphs, to microscale, where we can look at, for example, interactions of multiple molecules in our body, right, an interactome or a biological interaction network, all the way to the global scale, where we can model entire countries or even the entire world as social networks of interaction. between different people. So let me stick to this metaphor of a social graph as an example throughout this talk. And basically here we have a collection of people with their relations or interactions. So mathematically, these are nodes and edges of the graph. So edges are pairs of nodes, as you know, and we will assume that we have node-wise features. Just for simplicity, modeled as d-dimensional vectors. Okay, let's say that these are demographic properties of the users in our example. We can, of course, make it infinitely more complicated. We can add categorical features. We can add features to the edges as well. But just to keep it simple, let's stick to this particular setting. Now, what you need to understand about graphs in this context is that we don't have a canonical way to order their nodes. So basically, the set of nodes is a set, and sets are unordered usually. Okay. So when I write this numbering of the nodes 1, 2, and so on, this is actually cheating. So I automatically prescribed some order. And it is very convenient because I can, for example, now take the node features and arrange them into a matrix, right? Each row here represents the d-dimensional vector of a node. And I can also represent the graph itself, the structure, what is called the adjacency matrix, as an n by n matrix, where we have 1 in a position where there is an edge and 0 if there is no edge, right? Now, the choice of the order basically changes the structure of these matrices. I can arbitrarily permute the nodes of the graph, and this will change the order of rows in the feature matrix and the order of rows and columns in the adjacency matrix. So what we see here is that there is a permutation matrix that acts on these matrices. Now, so the permutation matrix here is a representation of the permutation group. You can actually see also that it acts differently on different objects, right? So it acts on vectors by multiplication from the left and on matrices by multiplication from the left and from the right by the transpose. So permutation is a very large group. It has n factorial elements. So we'll see that it will actually impose certain limitations on how we can work with graphs. Now, if you want to implement a function on the graph that provides a single output for the entire graph, like in our example of predicting properties of molecules, we don't care about the way that we order the nodes, right? So we want a function that is unaffected by the action of the permutation, and in other words, a function that is permutation invariant, right? So this is a mathematical condition for permutation invariance. I permute the inputs, and now the graph itself is also part of the input. This is very important. And we get the output that looks exactly the same. If I want to do node-wise predictions, so something analogous to the image segmentation from the computer vision example, or let's say I want to detect some bad users in a social network, in this case, I output node-wise representations. And in this case, I want the function to change in the same way as the input with the ordering of the nodes. So in other words, this function is permutation equivariant. So you see that there is this matrix P here that appears. And if you look at the typical graph neural network, as you've seen from the previous lecture, I hope you can immediately recognize an instance of our geometric deep learning blueprint, where we have the permutation group as our geometric prior, the graph is our domain, and we have a sequence of permutation equivariant layers. So these are the propagation or diffusion layers of a GNN. Optionally, a global pooling layer if we want to produce a single graph-wise readout. And also, in some architectures, we have local pooling layers that are obtained by some form of graph coarsening that can also be made learnable. Now, the core operation of graph neural networks, at least the most common type of message passing based graph neural networks, is considering a neighborhood of a node. One of the reasons why we cannot do more general things, well, first of all, we probably heard about higher order graph neural networks, but it becomes computationally intractable. So this is a kind of simple trade-off. We'll see, of course, that we run in this case into some limitations and what kind of functions we can express. So bottom line, we take a node, we look at its neighbors, we take the feature vectors of the neighbors, They form a multiset, so it's a set where the same element can be repeated more than once because we might have identical features at neighbor nodes. And together with the feature vector of the node itself, we need to aggregate them by some function that I denote by phi. So this is what is called the local aggregator. Now, because we don't have any canonical ordering of our neighbors, as I remind you, is the situation in graph, we must apply a permutation invariant aggregator. Now, we do this for every node of the graph. So we get as an output a matrix of feature vectors at every node that is permutation equivariant, right? If I change the order of the nodes in the input, in the output, they will be changed exactly in the same way. And the choice of this aggregator is extremely important. You already heard the mention of the Weisfeiler-Lehmann graph isomorphism test, so we'll get to it in a second, and I will remind you what it is. So there are multiple ways that this function can look like. So these are the different flavors of graph neural networks. So typically we have some permutation invariant aggregation operation, like sum or maximum or average. We have some learnable functions that transform the features of the neighbors and then the aggregated output. And there are many nuances into how these different components are chosen or designed. So the three main flavors are the convolutional flavor, where we have an aggregation that is dependent on the structure of the graph, but not the features themselves. So the simplest example is just summing up our neighbors. And as we'll see, this leads to the classical convolution. We can also have the attentional flavor, where it is still linear aggregation, like summation in most cases. But now the summation coefficients depend on the features themselves. So this is the most commonly used architecture from this class is the GATT, graph attention network. And the most general flavor is general message passing, where we have nonlinear functions that depend on the feature of the node and the neighbor. So more general doesn't necessarily mean better. Of course, more general message passing neural networks demand more computation and more memory. So sometimes being simpler is preferable and sometimes also better interpretable. So as I mentioned, graph neural networks are intimately related to the Weisfeiler-Lehmann test. So it's already a classical algorithm that was developed by Andrei Lehmann and Boris Weisfeiler, two Soviet mathematicians in 1968. And this is an algorithm that attempts to test whether two graphs are isomorphic, or in other words, they have the same connectivity up to the reordering of their nodes. So it's actually interesting that the problem originally was posed to them, according to the legend at least, by a chemist, George Viladuz. And he probably deserves also the credit of being the first to model molecules as graphs as early as 1963. And I think in the West, this honor goes to Morgan with the eponymous molecular fingerprints. So what Weisfeiler-Lehmann does, it's essentially an iterative color refinement procedure. It starts with a graph where all the nodes have the same color, and by color here I mean a discrete label. And essentially it looks at the structure of a neighborhood, basically a node and its neighbors, and injectively assigns them new labels. So neighborhoods with different structure will be assigned new colors. So here initially we have two different neighborhoods, right? We have a blue node with two blue neighbors and a blue node with three blue neighbors. So these will become green and yellow. And we can repeat this procedure again. So now we'll have three colors. At some point the colors will stop changing, at which point we output their histogram. And this is a kind of a descriptor of a graph. So if I give you another graph and I get a different histogram of colors, I can for sure say that these graphs are not isomorphic. But if I have the same colors, actually I cannot say it for sure, because this is a necessary but insufficient condition. So we can find examples like shown here of graphs that are not isomorphic, but they would be indistinguishable from the standpoint of this algorithm. So this is the situation where we say that the WL test fails. Now it was shown that graph neural networks are equivalent to the Weisfeiler-Lehmann test, or in the sense that they are not more powerful, meaning that anything that can be distinguished by the Weisfeiler-Lehmann test can be distinguished by a graph neural network, and there are no other graphs that cannot be distinguished by WL that can be distinguished by graph neural networks. And the crucial condition for this equivalence is the injectivity of the aggregation function. So sum, for example, is a good choice, whereas minimum or maximum is not. Now, let me say a few words about some interesting special cases of graph neural networks, and then we'll move to other objects in our zoo of different domains. So one interesting case to consider is a graph with no edges. So it's just a set which shares the same structural characteristic of being unordered with graphs. And here we can do two things. So first of all is to consider each element of the set entirely independently, process it independently by applying a shared function phi to the Fisher vector of each node. And this becomes a permutation equivariant function over the set. It's a special setting of the graph convolutional network with an identity adjacency matrix. This is what is known as deep set architecture in machine learning, or point net in computer graphics, where it was devised simultaneously for the analysis of point cloud data. Now, another extreme is, instead of considering each element of a set individually, we can assume that any two elements can interact. So in this case, we have a fully connected or a complete graph. And you can see that in this case, actually, it makes no sense to use the convolutional flavor of the graph neural network, because the aggregation will be over the set of all nodes. So this second argument will be the same for all nodes. It will be redundant. So we'll need to use at least the attention flavor, and we can interpret it as a kind of learnable soft adjacency matrix. And I hope we can recognize the famous transformer architecture that is now the bread and butter of natural language processing. You can also see that this is a special case of graph neural network, where the graph is learned in the form of this attention. So I should say that there is a little bit of cheating in this, maybe a slightly simplified analogy, because the transformers are used an example where actually we do have an ordering of nodes. They usually apply to sequences, like sequences of text. And typically this positional information comes in the form of additional feature vectors attached to every node that are called positional encoding. That you covered in the previous lectures. And this is a kind of extra vectors that uniquely identify the nodes. So same things can be done for graphs. So there are multiple ways of doing positional encoding, and we'll talk about it in the second part of the lecture, and also in several follow-up lectures. So here is one example of how you can count structures to do what we call structural encoding. So here you can identify the node by whether it participates in certain low-level structures, such as triangles or cliques. And this way we get essentially the standard message passing architecture that is enriched with some structures that are inaccessible to vice-relevant tests. So we can show that it's strictly more powerful than the WL test with appropriate choice of substructures. And where we see it prominently, this was actually a precursor of an entire class of networks that emerged this year, and Fabrizio will talk about it in his lecture. This is a way of incorporating interesting problem-specific inductive bias, like in organic chemistry. We have graphs with a lot of cycles. So these are, for example, aromatic rings in molecules. And the molecule of caffeine I showed before has a ring of size 6 and a ring of size 5. So if we count these structures and provide them to the graph neural network, this architecture we call the graph subtraction network, we see that our ability to predict properties of molecular graphs increases very significantly. And again, I will not steal the thunder from Fabri, so this will be covered in his talk, how we can use these ideas of subgraphs to increase the expressive power of graph neural networks while remaining in the remit of message passing. Now, another thing that is also prominent in modern graph neural network architectures is the trend to decouple the input graph, which is part of the input together with the features, from the computational graph, basically how we propagate information of these features across different nodes. And again, here in the second lecture, I will offer maybe some more interesting geometric principle perspective. So one thing that you can try to do is to, for example, to sample the graph. So this was done as a remedy to cope with with large-scale graphs. You can also try to do rewiring, so change the structure of the graph to propagate information, or use filters that not only look at the immediate neighbors, but also the neighbors of the neighbors, so multi-hop filters. An analogy in images would be to look at convolution with a bigger window. And you can also learn the graph, so it can be optimized for the downstream task. And this is typically called latent graph learning. And you can make all this construction of the graph differentiable and back propagate through it. So the graph is updated between different layers of the neural network on the fly. And probably the first instance of such architectures was a dynamic graph CNN. So it was my collaboration with colleagues from MIT. We use it first for computer graphics architecture, and then recently with collaborators from TU Munich for disease classification in neurodegenerative diseases. So let me now move to grids, and grids are essentially a particular case of graphs, but they have more structure, and therefore they give rise to probably more recognized operations that we all know. So first of all, you can see that a grid with periodic boundary condition, where we wrap around things, right? So we connect the last node to the first node, is what is called the ring graph. And one thing that you notice on a grid compared to general graphs, that first of all, we have a fixed neighborhood structure. So in this example, each node has exactly 2 neighbors. But not only that, we have the order of the neighbors fixed, right? Or I can always talk about the neighbor before and the neighbor after. And I remind you that in our design of a permutation equivariant function, we used a local aggregator that acts on a multi-set of our neighbors, right? Because we don't have an order for our neighbors. On a grid, we do, so we don't need to make this aggregation permutation invariant. We can actually make it look like this. So we have an ordered sequence of inputs to this function, and if we make it linear, we get the classical convolution. So that's exactly can be represented in matrix vector form as a circular matrix, where we have this very special structure. It's a matrix with multiple diagonals where the elements on diagonals are equal, right? So these are called circular matrices. It's synonymous with convolution. And a certain matrix can be obtained by taking a vector and appending cyclically shifted versions of these vectors. So these are exactly the shared parameters that I mentioned in the beginning. So these are the weights of a convolutional neural network. Now, what is special about convolutions or circular matrices is that unlike the general matrix product, which is not commutative, or in other words, AB is not equal to B, it is actually the case for circular matrices that they commute under multiplication, right? And in particular, they commute with a special circular matrix that cyclically shifts the elements of a vector by 1 position. So this is the shift operator that I mentioned in the beginning as well. So circular matrices commute with shift, right? They commute with each other, in particular with one special circular matrix that is the shift. And this is just another way of saying that convolution is a shift equivariant operation. I can first apply the shift, then convolution or vice versa. The result will be the same. So this statement works in both directions. It is easy to show. Not only every circular matrix commutes with shift, but also every matrix that commutes with shift is circular. So what we get from here is that convolution is the only linear operation that is shift equivariant. And here comes the power of our geometric approach, that convolution automatically emerges from translational symmetry. So the only thing that I assumed here is I want it to be equivariant to shift, and I get the convolution as a result. So I don't know how about you, but when I studied signal processing, somehow convolution was given as a formula out of the blue, and when I myself taught deep learning, CNNs are explained by appealing to this analogy to organization of neurons in the brain. So here is how to derive it axiomatically from first principles. So here's another nice thing. So we know from linear algebra that commuting matrices are jointly diagonalizable. So they have the same eigenspace, or in this case in particular, right, which is slightly cheating, but nevertheless it works here because we don't have multiplicity of eigenvalues. we can find a common basis in which convolutions amount to pointwise products, so they become diagonal matrices. And because all circulant matrices commute, we can pick one of them just for the convenience of analysis, and it's easy to look at the eigenvectors of the shift. So basically, we can say that all commuting matrices or all convolutions are jointly diagonalizable by the eigenvectors of the shift, and we can actually derive the eigenvectors of the shift analytically. And surprise, surprise, it happens to be the DCT basis, right? So the cosines that form the discrete Fourier transform. And the eigenvalues are actually given as the Fourier transform of the vectors of parameter theta. And you see that even the Fourier transform comes from this fundamental principle of symmetry. And if you're familiar with representation theory, this is related to the notion of what is called irreducible representations. And this relation between convolution and the Fourier transform is called the convolution theorem in signal processing. It gives two ways of performing convolution, either multiplying by a circulant matrix, so this is corresponding to the sliding window, right, across our signal, or in the Fourier domain as element-wise product of the Fourier transforms. And this can be done efficiently on grids because we have multiple fast Fourier transform algorithms. So in graph learning literature, some of the first works originated from graph signal processing that tried to generalize convolutions on graphs using the notion of graph Fourier transform, the eigenvectors of the graph Laplacian. And this is, for example, the work of Michael de Ferrar on Chebyshev networks. So let me now move to a more general case where our group formalism will become more prominent for the first time. And again, let me remind you of convolution, still on grids, that we've seen before. We can think of it as a kind of sliding window or pattern matching operation. So I can take a block of pixels from an image, multiply it by some filter, and move now this window to different positions in the image. So let me formalize it. I define a shift operator that shifts the filter that I denote here by psi, an inner product that matches the filter to the image. And if I do this inner product for every shift, I get the convolution, right? So basically, for every different position of the filter, I get how correlated it is with the image, and this will be the output of the convolution. Convolution or correlation depends on how we define whether we invert or reflect the filter or not. Doesn't really matter here. Now, the special thing here is that it is cheating in the sense that we assume the translation group and we identify it with the domain itself. So you need to understand that the group is a very different animal from the domain itself. But in this particular case, there is one-to-one correspondence because I can identify a translation with a point on the domain. I can describe saying that I translate to point u by basically defining this t with subscript u, right? So the shift moves to the point u. But this is obviously not the general case. So in general, we have the filter that is transformed by the representation of the group, rho of g, right? And now we need to compute the output of this inner product for every element of the group G. So if I took the same grid and I chose, for example, the rotor translation group, or in addition to translations I have rotations, it has a very different structure. I cannot do any more what I did before, right? So the convolution, the output of the convolution might live in a very different space, right? So here's an example. We show how to do conversion on the sphere. And in this case, the sphere is S2, right? It's a two-dimensional manifold. We can define points on this manifold basically as unit length three-dimensional vectors that I denote by U. Now, the group that we consider here is what is called the special orthogonal group, or SO3. So these are rotations that preserve orientation. I can describe them by matrices that are orthogonal and have determinant 1, right? I denote them by R. Now, basically, in order to compute this convolution, we just need to run the filter across the image for every possible element of the group. But this group, actually the SO3, it has a different structure from the original domain. So if the sphere is a two-dimensional manifold, SO3 is a Lie group, so it has a manifold structure, and it is a three-dimensional manifold. And the way to see it, you can see it in this little picture. I can rotate on the sphere three ways. I can rotate this way, I can rotate this way, right, along meridians and parallels, and I can also rotate around itself, right? So the smiley also can rotate around itself. So these are 3 degrees of freedom, or 3 dimensions, whereas the sphere itself is two-dimensional. So the output of the convolution on the sphere will live on SO3, on the three-dimensional manifold. And if I want to do another layer of convolution, I will need now to do it on SO3, right? So I will need to do it on this manifold, and here the points will be rotation matrices, denoted by Q. Okay? So this is a very important distinction. So the Euclidean convolution is actually a very special case. Now, even this space, the sphere, is a very special case. So it is a manifold, so it's a non-Euclidean object, but it is quite special. So every point on the sphere can be transformed into another point by an element of the symmetry group of rotations, and in geometry we call such spaces homogeneous, and their key feature is that the transitive action of the group, or some kind of global symmetry structure. And this global symmetry structure doesn't obviously hold for general manifolds, so here will be the last class of objects that we'll be considering, and these are manifolds. Now, manifolds are, in machine learning, maybe less so in the past couple of years, but in general they are exotic objects, right? So why do at all we are interested in manifolds? So I will give you 2 motivations. So one of them is that in computer graphics problems where we consider 3-dimensional objects, in many cases we don't care about what happens inside. So we can use, of course, we can rasterize a 3-dimensional volume and consider voxels instead of pixels like we do in images, but in this case we will waste a lot of representation, right? So if I'm interested only in the surface of the bunny, I don't care what happens inside, right? So there is a lot of wasted information here. Another reason is that manifolds have a very convenient mathematics that allows to model their deformations. And this is very common, again, in computer graphics, where we need to deal with deformable objects, like human body or human face. And one interesting manifestation where both of these reasons come together is the modeling of proteins. So in protein modeling, we want to abstract out the internal structure that might be very complicated and intricate, like basically, if you heard about protein folding. What is accessible to molecules that interact with the protein is only the outside surface. So the internal fold is of no interest. And also, the deformation, proteins deform when they interact. So these deformations are important to take care of using this surface-based representation. So when we compare to the previous example of a sphere, we had a global symmetry group, right? So I had a canonical way of getting from one point to another. Basically, I had an element of the group that moves me from point U to point V. On a general manifold, we don't have this global symmetry group structure. I have many ways of getting from point U to point V. So let me visualize it slightly differently. So this is from Maurice Weiler. That's a beautiful paper about non-Euclidean convolutions. So here's the situation in the Euclidean case. I can think of convolution as taking some local filter and moving it around. And I always have, no matter how I go from one point to another, I will always get to the same result, right? So the red and the green path produce the same filter. On a non-Euclidean domain, this is not necessarily the case. Here, the result of what we call parallel transport is path dependence. So if I go from this point to this point along the red line or along the green path, I will get a different orientation of the filter. And here's another example. So this is a non-orientable manifold, the Möbius surface. So if I go along the green curve, or if I go along the red curve, I will get the filter flipped. I will get a reflection. So this is just to visualize that on general manifolds, we don't have this luxury of moving a small thing around. We need to be more careful. Now, on manifolds, we actually have 2 types of invariants. So the first one is this local choice of a system of coordinates, what is called gauge transformation. And the second is the global deformation itself. So I can deform the manifold itself. So we actually didn't talk about it, but this is an important concept of what we call geometric stability, that if the domain itself changes, we want the output of our neural network architecture or a function that we compute on this domain to be stable, not to change abruptly. So we want it to be somehow continuous or smooth with respect to the deformation of the domain. So this, both of these conditions can be achieved on the manifold. So let me just give you a very brief overview of the difference between manifolds and Euclidean spaces. So the first crucial difference is that manifolds are only locally Euclidean. So these are topological spaces where you can take a point, a small neighborhood, and map it to a Euclidean space of certain dimension. If this dimension is D, we say that the manifold is D-dimensional. So it's convenient to talk about two-dimensional manifolds, which are surfaces. So in this case, every point or every neighborhood of a point is homeomorphic to a plane, which we call the tangent space or the tangent plane. So the tangent space can be equipped with additional inner product structure that is called the Riemannian metric. It allows us to locally measure lengths and angles. And if I deform the manifold in a way that is doesn't affect the metric, so all the properties that are expressed in terms of the Riemannian metric are called intrinsic, then we call such deformation an isometry. So isometry means metric preserving deformation. And isometries also form a group. So if I compose two isometries, I get another isometry. Now, we can define naively an analogy of convolutional manifolds using this metaphor of a local filter that is applied in the tangent space. So you can see it here. So I can define at every point this filter. I will use what is called the exponential map. So it's an intrinsic map allows us to express the signal locally in the tangent space. So it's a map that goes from the tangent space to the manifold. Now, if I define the filter in this way, basically it is intrinsic. It is invariant to isometry. So if I start deforming my underlying domain, I will get the same result. And this was the first design of convolution-like architecture on manifolds that we call geodesic CNN. So that was a work from 2015. And here you can see how these different filters look like. The problem is that there is a little bit cheating here as well. And one important thing that I didn't say is that because we are forced to work locally on the manifolds, we don't have a global system of coordinates. Now, what it appears here in this integral, these are abstract vectors. So I cannot actually represent them on the computer, right? And you need to understand that usually when you're explained what vectors are, at least at school or maybe in basic courses, so there is this crime against humanity that is committed, that you are told that you can think of a vector as an array of coordinates, array of numbers, or an arrow. So actually, neither of these is true. So vectors are neither arrows nor arrays of numbers. Because if you think of a vector as an arrow, you already prescribe a direction. So it's not a vector space. You have an extra structure in the form of inner product. It's only inner product that defines directions. You can also not think of vectors as an array of coordinates, because in order to do it, you need a basis with respect to which you express vectors. So vectors are standalone geometric abstract notions. This is what makes abstract algebra so great. But bottom line, in order to work with vectors on the computer, we need to represent them with respect to some frame, or as physicists call it, a gauge. So gauge is just a collection of smoothly varying local frames in the tangent space on the manifold. And if we represent them with respect to the frame, we have this ambiguity of a gauge transformation. So we can define this gauge up to an action of a group. So this is called it's a local symmetry group that is called the structure group. And we have multiple ways of transforming our local reference frames depending on how much structure we have in our object. So if we are talking about naked manifold without any Riemannian structure, basically it's just a topological space. So here, any invertible matrix can change our frame arbitrarily, right? So we are talking about the general linear group. If we have manifold with orientation, we can talk about invertible matrices with strictly positive determinant. If we have a volume form, we can talk about preservation of the volume, right? So we can constrain the determinant of this transformation to be one, what's called the special linear group. If the manifold has metric, we can talk about orientation. So we can preserve orientation by orthogonality. So we're talking about orthogonal group. And we have an orientable Riemannian manifold. So we rule out pathologies like the Möbius surface. We're talking about orthogonal mixtures with determinant equal to 1, or the special orthogonal group that we've seen before. And finally, if we have a manifold with a frame field, we don't have any ambiguity. So it's a trivial group with just the identity element. So in practice, we are talking about surfaces, so we get this situation where we need to deal with SO2. So if it's a surface, it's a two-dimensional rotation, so we don't know how to choose our gauge locally, and we can construct a gauge equivariant filter that will be, the output will be transformed, it will be rotated in the same way as the rotation of the gauge in the input. And I should say that there is a point here that where theory diverges from practice. So in theory, we know that we cannot construct a smooth gauge on something that looks like a sphere on the manifold that is topologically equivalent to the sphere. So this is sometimes called the hairy ball theorem, or the more correct term is the Khwopa theorem, that tells you that there is a non-vanishing smooth field on a sphere-like manifold. So metaphorically, you can say that you cannot comb a sphere. So if I have hairs, if I try to comb myself, there will be at least one point where there is a vortex. This also explains why on Earth there is always one point where there is no wind, because wind is also a tangent vector field, and it must vanish by virtue of this theorem. In practice, we can define stable gauges that might vanish in a few points, but still they're very stable and can be repeatably computed. They're deformation invariant. So if we want something that is cheap and dirty and works in practice, this would be a way. So what we gain from this perspective is an intrinsic convolution that is defined on the domain itself. It leverages this more efficient representation of three-dimensional objects as a surface. It is deformation invariant. It will require way less parameters. It has some designed properties that make it nice and stable and convenient. So I see that I'm running out of time, so let me go directly to conclusions, and then we talk about some more advanced stuff in differential geometry. So we've seen these 5 geogeometric deep learning, so different domains on which I can define deep learning architectures, following the same blueprint, basically defining our domain, defining the symmetry structure through the group, and then defining equivariant transformations or equivariant functions on this domain. And we've seen that many architectures can be derived from this blueprint. I didn't cover some of them, but I guess you can read about this yourself in the book. And this is really probably the beginning of this field. Well, it has very deep roots, but I think only now it has become exciting and practical in many applications. One field that I'm particularly excited about is structural biology, dealing with proteins and designing drugs, for example, new molecules that bind to these protein targets. So we've seen already some revolutionary results like the AlphaFold 2. It's actually probably one of the triumphs of geometric machine learning, because one of the key elements of this architecture is what they call point invariant attention. So this is an equivariant message passing type graph neural network, if you look at it from our perspective. And let me finish with a quote from Helvetius, that once said that the knowledge of certain principles compensates for the lack of knowledge of certain facts. And I think the entire approach of geometric deep learning is exactly this. So if you know some principles, you can derive specific architectures from these same principles. So I will stop here. Maybe let's make a 5 minutes break, and then we move to the second lecture. And I apologize in advance if it will take me a little bit more time to cover it, where we'll be looking again at some architectural designs of graph neural networks, such as positional encoding or graph rewiring, and try to derive it from first principles again. Thank you.
Sure. Thank you very much. Yeah, let's take a break for 5 minutes. And this was a wonderful presentation, and for all of the students and participants listening, I mean, it's a very influential framework because it allows to understand a lot of different architectures under one simple, in a more principled way. And I'm sure many of you will catch up on the details that is present in the book as well. So let's proceed for the next session in maybe after 5 minutes. Okay.
Thank you.
Thank you.